I finally fixed the surface finish problems I was having with my 3D printer, and I learned a bunch of new things from your comments. Stick around. Welcome back to Cloud 42. I'm James. A couple of weeks ago, I put up a video showing how I made this tap guide block. And as you can see, I've been playing quite a bit since then. And the problem that I ran into on this is I had some really ugly surface finish issues. And if you kind of look at this up close, you can see what's going on. You can see all these kind of little zits and pimples on the outside of the part. This is commonly referred to as blobbing. And I asserted in the video that I thought the problem had to do with the 3D printer and the amount of G-code that was being pushed to it. And I got a bunch of comments on the video telling me that there's no way that's a possibility, and the problem is just that my filament is wet and it's popping and bubbling because of moisture in the filament. Now, that is actually not the case here. As it turns out, where I live in Idaho, the weather is very dry. There is not a lot of humidity in the air, and in fact, in the years that I've been running 3D printers, I have never had to store filament with desiccant. I've never had to store it sealed up. I can leave rolls, at least with ABS and PETG and various kinds of TPU and TPE filament. I can leave those out in the air indefinitely, and they don't pick up enough moisture to cause any problems. I don't know about PLA. I don't really print with PLA. I actually have one roll, and I printed with it a couple of times. I'm not real happy with the properties of the plastic, so I don't use it. This is ABS, and while this surface finish does look similar at this scale to something that you get with moisture, the real issue that I was having was an issue with G-code flow to the printer, and that did turn out to be the problem. So when you print an object like this, the sides are not actually flat, and the G-code that goes to the printer is not telling it, okay, move in a circle. If it did, you'd have basically one line of G-code that defines the move around the outside of the perimeter, but that's not what we have. We actually have a large number of facets around the outside, and so what ultimately is sent to the printer is G-code telling it to move in a sequence of straight lines around the part. And those flow very, very rapidly to the printer, and the more there are, the smoother the surface. However, the more there are, the more G-code the printer has to process in the same amount of time. If I'm moving around the perimeter at 100 millimeters per second, and there's 100 lines, actual line segments here, the printer has to process all of those while it moves around at speed. And if you get a buffer underflow or a buffer underrun, which means that the printer caught up and it hasn't processed the G-code for the next line, it'll pause and stop for a moment, and that's exactly what was happening. And so I got some comments saying, don't make assumptions, it's just moisture in your plastic, which of course I might point out is an assumption that was incorrect. But I wasn't actually making an assumption when I stated that, because I was observing the printer and watching what happens. And so the head comes down, and when you're printing the perimeter of a part like this, what you would assume, and what I always see, is a nice smooth movement, and you can hear it as you're moving around. And that's not what I was seeing and not what I was hearing. What I was hearing was this more and it was stopping. The sound effects are free, by the way. It was stopping at various points around, and it was just sort of random. And you could see that every place where it stopped, the pressure in the chamber doesn't stop suddenly, and so the plastic continues to flow a little bit, and you get a little blob. Now, I had recently, this problem was brand new, and I had recently added some displays to my printer, and I was running a bunch of new plugins to support Octodash, which is a nice little touchscreen controller for Octopi on the 3D printer. And I went in and removed all of those plugins and uninstalled Octodash, and lo and behold, the printer returned to its previous behavior. And you can see, here's a part printed afterward, and you can see that this surface is just glassy smooth. And what happened is it's no longer having buffer underruns, and it's no longer pausing. And so now the surface is nice and smooth. So if you see something like this on your printer, this kind of surface finish, you can absolutely check and make sure your filament's dry. That's always a good thing to make sure of. But if you're using Octoprint or Octopi, you might be experiencing the same situation I was seeing, where I was having buffer underruns and pauses, which was causing the surface finish. And the problem is even more pronounced down inside the bores. You can kind of see the inside, just how rough those are, and that makes it even harder to control the inside dimensions. Compared to after fixing it, you can see the insides of those are nice and smooth. The only thing you see are the normal surface variations that you have from the kind of start and stop points of printing those perimeters. So that's what was going on with the surface finish. That's now fixed. I was pretty sure it was something in software because it had just started. And these were printed with exactly the same roll of filament. I never dried it. I just fixed the software and reprinted, and it solved the problem. Now, I also got a whole bunch of comments about Fusion 360 and the way I was constraining the sketch. And there were actually a bunch of really good suggestions. Now, certainly the way I did it worked, as evidenced by the fact that I'm holding the part in my hand, but there are 100 different ways to do things, and a bunch of the suggestions that I got were actually really constructive, and I learned a bunch of things, and I think if I were to do this all over again, I would do it differently based on what I learned. So let's go into the computer and do it differently based on what I learned. This is the model that we designed last time, and if you haven't seen that video, I will put a link down in the video description. You can go check that out. Let me open the sketch here. This is the sketch that we used to design the part, and of course it's just one sketch and then it's extruded vertically. And to control this sketch, we created an outside circle and then a circle offset inside that by, in this case, 100,000ths of an inch, something to give us a controlled web thickness, and then set all of the circles inside of that and made those tangent, and then drew construction lines between the centers of all the circles, and then lined up short line segments between them, set all those equal, and let the sketch layout constrain this. And there's a few problems with this. One is that it ended up just by chance that the web thickness between the holes was similar to the thickness of the outside wall. It probably would have been better to constrain the distance between the holes and the distance and the thickness of this outside border, and just set those equal, and then let the sketch determine the outside dimension. And we'll do that here in a minute. The other issue is that because I created the construction line and then created these short line segments in between the circles in order to be able to set them all equal to constrain the distance, I created a problem for myself trying to select these, because depending on exactly where I line up the mouse, sometimes it selects the construction line, sometimes it selects the solid line. And you can just click and hold and then pull down, and you can choose which thing you want to select, but it's kind of a pain. I had some people in the comments suggest that you could use the selection filter to just filter out construction lines. And I took a look through the selection filter. I couldn't find a setting for that. I did some reading, found a lot of people requesting features like that, but nothing like that appears to exist. If it does, go ahead and throw that down in the description and explain that to me, and I will be happy to pick that up and put that as another tool in my toolbox. In the meantime, though, let me show a couple of other things that people suggested that ended up being much better options. So let me just start by taking out all of the lines that are here now. And since I'm just deleting, it doesn't matter which ones I select first. And instead of constraining the outside of the circle, I'm going to let that float. And I want to do a couple of other things here. I want to actually use some parameters. So I want to use parameters for everything so that I can easily modify this later. So let's start with the web thickness, and let's set that to 100 thou. And that'll be both the thickness between the circles and the thickness of the outside web as well. And let me add another thing here, which is the hole adjustment. And I'll currently just set this to 0, but that'll give us something that we can use to adjust the size of the holes to compensate for issues with 3D printing. And we'll get to that in a little bit. And then I'm just going to go ahead and set up the different hole sizes. hole 1 is 1285. Okay, so I've got all of these entered, and I actually forgot my hole adjustment. So I'm going to go back and add the hole adjustment to each one of these. And in fact, just to make this easier to type, I'm going to change the name of this to just adjustment. Okay, so there are all our parameters, the diameters for all the holes and the web thickness. Now let's apply these. So double click this dimension, and this is going to become hole 1, hole 2. Okay, that puts parameterized dimensions on all the holes. So we can come back and change these later. If we want to make a metric tap guide, we can just go and change those values. Now I want to go in and set the web thickness. Let's start with this outside dimension. This is an offset that's currently set to minus 100 thou. We'll change that to minus web thickness. So we can adjust that in the future as well. And now we just need to set the dimensions across between the holes. Now there are a couple of ways that people suggested doing this. One was kind of clever, and that is to just simply break the line instead of drawing another one over it. So I'll create a line across between these, and of course you would do the same thing all the way around, and then come in here and say modify break, and you select the line, and now it will break it into 3 segments. Then after I've done this all the way around, I can click easily the center lines that between them, set them all equal, and set them all to some dimension. And that will work. The one downside is that since it's broken, they're no longer collinear, and so these will move around. So you then have to add a collinear constraint between them first and do that all the way around before you then set up the constraints to keep the hole spaced. And in practice, that works, but it is cumbersome and creates a whole bunch of other things you have to do. Another way that I found you can do this without having the selection problem between the 2 different types of lines is to just create a line between these and, of course, create the lines all the way around. I won't do it at the moment. And then you can come back and just place points. So instead of breaking this into 3 segments or drawing another segment over here and trying to select it, just set points at all of these intersections. And then it is possible to just hit D for dimension and just set a dimension between those tangent points and set this to web thickness and do this all the way around. And then once you actually get the last one in there, then the overall size will snap to the correct size. Now there are some problems with this. I have had cases where the solver suddenly tried to move the dimension around. As I put the dimension in here, you can see you can have it in line with the line segment. You can have a horizontal dimension. You can have a vertical dimension between them. And I have seen the solver actually switch between those in order to try to solve, which is not at all what we're looking for. So let me show another technique that somebody suggested in the comments that actually works really well. If I want to just set a dimension tangent to tangent, I'll just hit D for dimension. And normally, if you select a circle and another circle, it's going to create that center to center. But if I want it tangent to tangent, then I'll just hit D for dimension again. Before you click on anything, right click and say pick circle, arc, tangent. And then you can just click the 2 circles and it will give you the tangent. It'll attach to the tangent. So I'll click that, add web thickness, and then I will just go around the circle. Now, unfortunately, you have to reselect the tangent every time. And I'll just go around the rest of the circle here, and whoops, I forgot to right click. Now, when I do this last one, I expect that obviously this is too large. And so it's going to pull these circles closer together. And the only way the solver can solve anything is by changing the outside diameter of this circle. So let's see if that works. Now, this is something that I've run into a couple of times, and it will not let me actually dimension between these last two circles because it thinks it's going to over-constrain the sketch. Now, it's not actually going to over-constrain the sketch because there's nothing keeping it from shrinking, but for some reason, it is not happy with that. There is a solution, and that is to simply dimension center to center and then subtract off half of the sum of the diameters of the circles. So I'll click here and do a center to center dimension. So we'll make this web thickness plus the sum of this diameter plus this diameter quantity divided by 2. And of course it's messed this all up, put parentheses around it. So it's web thickness plus the sum of D12 plus D3 divided by 2, enter, and it solves. Now this dimension right across here, we can go ahead and put one in there if we want, circle arc tangent, and go between those, and you can see this driven dimension that it creates actually does show the 100,000ths exactly like it's supposed to be because I got that formula correct. So this is a little bit of a pain, and I think this is probably a bug in the solver. I'm not sure exactly what's going on there, but it does work. And now we do have a situation where we are free to modify the parameters and the entire sketch will change. So if I go in here and say change parameters, and I want to change something specific, like let's say I go off and measure these things and discover that I need to increase the size of all of the holes slightly, I can simply add an adjustment here. Say I need to add 3/1000ths, hit enter, and you can see the entire sketch has adjusted slightly. Let me make that much bigger. Let's add 30/1000ths. And you can see the whole sketch has now adjusted to compensate for that. Let's set this back to 0. And print one of these blocks and then go out in the shop and actually measure with pins and see what the sizes are so that we can put in a correct adjustment factor and just get a direct printed part that doesn't have to be reamed out. And actually it'd be interesting to find out, is the undersize error from printing these exactly the same for all of the holes, or is it gonna vary depending on the hole size? Let's print it and find out. So now that we have a part with relatively good surface finish on the outside and on the inside of the holes, we need to measure the size. And there's lots of ways to do this. You've seen me measure holes with this micrometer. And this device has 2 sets of measuring surfaces, has some carbide pins here, and it has some actual ground carbide pins embedded in these jaws. These are rounded, by the way. I did get some questions on if you measure an inside of a bore with these inside jaws, aren't you going to get a wrong dimension because these aren't curved? Well, the answer is these actually are curved because they are designed for measuring the inside of bores. Now, the problem with a tool like this, when you're measuring a 3D printed part, is that you're only measuring at 2 points. You're measuring directly across. And since the inside of a bore that came off of a 3D printer is going to have some roughness to it, you're just going to get a measurement at that point. You're not really going to know what the clearance diameter is of the hole. The best way to measure the clearance diameter of a 3D printed hole, assuming you're not going to ream it, is with a pin or something else that goes inside and contacts at multiple points. Now, something like a tri-mic is great that slides in. It has 3 jaws that expand, and those are wonderful, but they're very, very expensive, especially if you get a set to cover all the sizes you're going to need in a shop. They can be, hundreds of dollars each, and they only cover a really narrow range. And so I find that the easiest and probably most economical way to do this in the home shop is with gauge pins. a set of import gauge pins that cover, in this case, 61 thousandths to 250 can be had in the, kind of $100-ish range. Larger sets that go up to larger diameters can be a little more just because there's more material involved. But you can buy the different sets in the different ranges and build up over time. And so I find that these are really handy for measuring 3D printed parts because they give you a good idea of how a round object that's going to be placed into that functional hole is going to behave, because it's going to ride up on the high spots inside. And now that the surface finish in these holes is pretty good, this is a pretty accurate way to do this. So this smallest hole should be a little over 128 thou. So if I grab my 128 thou pin, it of course doesn't fit, because 3D printed holes, at least on hobby grade FDM printers, almost always print these a little bit undersized. So let's just grab a smaller one, 109. That fits easily. Let's go up 117. And that is just a little bit too tight. Let's go down to 114. That fits in easily. 115. And that's a very nice fit. It takes a little bit of pressure, but it goes all the way through easily. So I'm going to call that 115 thou. And I'll write that down. Next hole should be 140. But of course 140 isn't going to go. I'm going to guess 125. And that goes easily. 127. Easily. 129. It's a little bit too tight. 128. Yep, that's about right. So I'm going to call that hole 128 thou. Now, I won't make you watch it, but I already went through and measured all of these holes except the last one. My largest pin only goes up to 500 thou, and it fits easily with a little bit of play. So this hole is a little over ½ an inch. I can measure it with the mic, but I don't really trust that value. So let's just take the values of all the rest of these and see where that ended up. And I've already done that, and I've already entered all the values into a spreadsheet. And so I've got my actual values, my target values here, and my actual values. And if you look at these numbers, it's really interesting. I computed the error on these. So it's supposed to be 128.5, it was actually 115. It's supposed to be 323, it was actually 310. And I subtracted these and came up with the error. And this is interesting. 13.5 thou, 12 thou, 14.5, 15, 14, 13, 13, 13, 13.1. So I'm off by about 13 thou. In fact, the average of these is 12.8 thousandths of an inch. So 128 tenths. And this is really interesting because somebody actually made a comment about how to adjust for the inside of the hole, you have to subtract the nozzle diameter. Now, this is not even close to my nozzle diameter. The nozzle diameter is 0.4 millimeters, which is quite a bit bigger than this. But I did print with a layer height of 0.35 millimeters when I printed this part. And it's very interesting that the error here is very, very similar to the layer height. It comes out almost exactly. And so I don't know, I'd have to do more experimentation to find out if it's really that simple. I can just add on the layer height to the hole diameter, but I am going to keep an eye on that in the future and see how that trend works out. Anyway, we have our hole sizes, and it looks like a constant offset of around 13 thou will bring these holes to size, so let's go in and change them. Okay, now that we have the data for the hole sizes and we can see that our error is about 13 thousandths, I can just go in here and modify this sketch. And I'll just go here and modify the parameters, change parameters, my adjustment, change that to 0.013, enter. And the whole sketch sizes up to accommodate that. And all we have to do is just go print this again. Finish sketch, and here we have our part ready to go, and it's been resized, and it's automatically changed it's maintained the web thickness between all the holes, and we just scaled it up. If we wanted to do a metric one, we could just go back in and change the parameters for all of the holes to metric sizes, and boom, we'd have it. And in fact, I could probably leave that same 13 thou adjustment, and they would probably come out exactly on size. Now I want to go ahead and put some branding on this, put a name on it. So I'll go ahead and create a new sketch here on the top. And let's put some text here. And I'll just put in C42. Whoops, click in the box for C42, change the font here. Take that around, maybe some metallic. It's probably a little bit big. Yeah, something like that'll work. Finish sketch, and then I'll just come back and select that and say press pull, and let's press that in minus 0.7 millimeter. That'll be 2 layers. Okay. And there we go. Let's send this to the printer and see how it comes out. And there is the finished part. I'm pretty happy with how this turned out. It is certainly going to be good enough. This is the 5/16 inch tap that I plan to use with it, and put that into the 4th hole, and that is a pretty decent fit. Just a little bit of motion, which is kind of what you want, and actually if you push it down onto the shank of the tap, it's an almost perfect fit. You hear it squeak a little bit. So I think this is going to work just fine for its intended purpose. Now, is plastic the best material for a tap guide block? No, probably not. I had lots of comments, people saying, oh, you should make that out of metal, or you should make that out of steel, or you should push in hardened drill bushings. Those are all great things, and if I were trying to make an heirloom tool, I would absolutely do it that way. But that's not what I was trying to do here. What I was trying to do is tap some holes, and I needed a tap block right quick. So I ran to the computer, sketched up, hit print on the printer after a few minutes of work, and I went and did something else, and a couple hours later I had my tool and I was ready to go. I didn't have to order it, I didn't have to wait for it, I didn't have to spend a lot of time working on it. Now, I turned this into a video and an educational opportunity, so I ended up spending more time on it, and I had surface finish problems with the printer because of some changes that I made to it, and that made it take longer. But in the general case, I could spend 15 minutes sketching a part, hit a button, come back later, and I've got my tool and I can go on my way. And if this thing does wear out, I'll just hit print again because I still have the files, and I'll have a new one. So as a shop expedient tool, the 3D printer is a great way to make these things. Well, that's all I've got for you today. If you are enjoying these videos, give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. If you've got more tips that I've still missed, or if this is going to turn out to be yet another example of Cunningham's Law and I'm going to learn more from this video, go ahead and drop your comments down below. Thank you for watching.